Okay, today we talked about rotations. We mainly spent part of the time talking about rotations. We will actually do dilations the next time we meet in class, but I will go ahead and record the entire video today. So our objectives are to rotate images on a coordinate plane, recognize order and magnitude, determine whether a dilation is an enlargement or a reduction, and then also determine the scale factor for a given dilation. A rotation is a transformation that turns every point of a preimage through a specified angle. So when we talk about the specified angle, usually we'll talk about the 90 degrees or 180, but it's not limited to those two. And a direction, when we talk about direction, we're talking about clockwise or counterclockwise, and it'll be about a fixed point. Some of our points will be the origin, but others will change. Okay, so here I have an image. It's been rotated to give us this new, or I should say the pre-image rotates to give you the image, and because these are exactly the same size and shape, we can say that this is an isometry. On example 1, we're going to rotate the image 180 degrees about the origin. So we're going to rotate it about this point. We'll call these A, B, and C. And if we're going to rotate about the point 180 degrees, we talked about visualizing. We said this is quadrant 1 and 2 and 3, and this one's 4. And I said that if you could actually flip your paper upside down, that would show you where the new image would be. And so 180 degrees will then put us, it should put us somewhere in quadrant 2, our new shape. So if we had a ruler and a compass, or I should say a compass and a protractor, we would do this a little bit differently. The first thing that you would actually do is you would construct a line from A through the origin, and then with your protractor, or your compass I should say, you would measure the distance from here to here and then mirror it on the other side. So these two distances would be equivalent. In our case, we could actually use the Pythagorean theorem to find that length. And then once we find that distance, we can mark off our new point A prime. So A prime is located at 1, -1. The same idea exists for B. You would construct a line through the origin, since that's what we're rotating about. And then we would measure this distance from B to the origin and then mirror that distance on the other side, and that would put us right there. So we have a B prime here, which is over 5, down 1. And then I stopped for a second and I said, hey class, let's look at what B was. B is back 5, up 1. I said, let's look at these two ordered pairs and say, can you guys figure out a rule for this? So if I start out with an ordered pair x, y, like you did in B, what would it take to get to your B prime? It looks like you would switch the sign on x and switch the sign on y. So without using construction ideas, I said, can you now find C prime? Well, C is located at let's see, back 4, up 5. So if our rule applies, then our C prime would have the ordered pair 4, -5. Let's go ahead and graph that over 4 down 5 for our C prime. And there's our triangle. It has been rotated 180 degrees about the origin. Okay, example B wants us to rotate 90 degrees about the origin, so we still have this point. We're going to rotate it about the origin clockwise, so we're moving forward. And then I said visually to my students, if you want to see what this will do, you take your paper and you turn it a quarter of a turn, so you turn it on its side, and we were able to see that they would move it all the way to this quadrant here. So if we were using construction tools, we would measure the distance from A to the point about which we are rotating, which is the origin, and we would say this distance has to be the same if we go 90 degrees. So here would be 90 degrees. That's where we get our right angle. So our distance from A to the origin would have to be the same as the distance from the origin to A prime. So that would put our A prime right here. And A prime is located at 0, 1. Okay, we're going to look at B. The same idea. We would draw a line from B to the origin, and then we would use our compass to measure out 90 degrees. Here's my imaginary compass. And that would give us our right angle. And then we would measure the distance from the origin to B and apply it on this line, which would put us right there. So here is our B prime. And let's go ahead and label B prime. B prime is over 1, down 4. And then at this point I said, hey, can you guys tell me what B was? B was over 4, up 1. And I said, is there any way that we can make a connection between B and B prime? And so we said, if we start out with xy, that's what B would start out with. What would it take to get to B prime? So we said, hey, the 1's just flip places, so the y will come first, and the x becomes negative. So we said, can we use this idea to find C prime? Well, C starts out at 1, 5. So according to this rule, C prime, the 5 would be first, and the 1 would be last, and it would change the sign. So we'll go ahead and graph that over 5, down 1 to get our C prime. And that completes our triangle. And it has been rotated 90 degrees clockwise about the origin. Okay, our last one with our rotating is 90 degrees counterclockwise about the origin. So again, we're still going about the origin counterclockwise. Again, if this is quadrant 1, 2, 3, 4, we're going the opposite way of a clock, so we're going this direction, and just 90 degrees will put us in quadrant 1. So let's label these A, B, and C, and let's talk about A, or I would say let's move B first. It probably seems the easiest because we can actually count that distance. That distance is 5. And then we would make a right angle and count 5 there. And that would put B prime right there. So let me erase those and mark B prime. Okay, we're going to move A next. So A here, we have to go 90 degrees. That looks like about a right angle, and this distance has to match that distance there, so that will put A prime right there. We're going to go ahead and identify these points. A prime is 1, 1. B prime is over 5 up 0, and I'm going to compare A prime and A. A, I'll write it above, was located at 1, negative 1, and I don't know if this is the best one to compare, but by this time they started to figure out the rules. What happens with this rule is that if we start out with x, y, and we go ahead, we'll switch the y, and we actually change the x. I didn't write that right, sorry. The x stays the same, it's the y that's going to change on this one. So at this point we said let's identify what C is. C is located over 4, down 5, and according to this rule we'll switch and the y will come first and change the sign, so it would be positive 5 and x stays the same for 4. And that should give us our coordinates for C prime. So we'll go ahead and graph it over 5 up 4. And there is our triangle that has been rotated 90 degrees counterclockwise about the origin. Rotational symmetry is when a figure can be rotated less than 360 degrees about a point so that the image and the pre-image are indistinguishable. They look exactly the same. You can't tell the difference between them. So order is the number of rotations a pre-image can rotate and still produce an indistinguishable image. The magnitude is the amount of degrees the image must rotate to produce an indistinguishable image. So the magnitude is the amount of degrees they have to rotate. The order is the number of rotations. So as I look at these shapes, we're going to determine the order and the magnitude for each one. So the order is how many turns do I have to turn this, or how many turns can I turn it in 360 so that I get a shape that's exactly the same as the shape that I see. We talked about if we flipped it over and then flipped it again, we get 2 rotations where it's exactly the same. And we said how far is one flip if we flipped it over. We talked about that as being 180 degrees. Okay, our next shape, and we did start talking about if we could draw a circle, oh that's terrible, a circle around our shape, there you can't even see it. And we talked about how many times, if it's a regular shape, how many times does it touch our circle? Here it would touch it 6 times. Then we would say that it has 6 times that it can rotate within 360 degrees. And then to find that magnitude, we take the 360 divided by 6 to get 60 degrees. On our second shape, we said we would have to turn that 360 degrees for it to be indistinguishable. So we said this has no order or magnitude. On our star, they're all the same. We took the same idea that you could draw a circle and then talk about how many times it touches the circle. Here it would touch 5 times, so we would say it would have an order of 5. And then we take 360 divided by 5 and we get the 72 degrees. Okay, a dilation is a transformation that may change the size of a figure. It's a similar transformation. That means it has the same shape, but not necessarily the same size. So here I have a shape, it's gotten smaller. We talk about a scale factor, and we use the letter R to represent the scale factor. This is the amount of change for either an enlargement. If your number is greater than 1, it's an enlargement, or a reduction, where it's less than 1. And this shape up here would be considered a reduction from our pre-image to our image. To find R, you're going to compare the length of a side of an image to the corresponding side length of the pre-image. So you got to remember that you're taking the image to the pre-image, and you're going to compare those lengths. There's other ways to find R, but this is how we're going to do it here. So here we have triangle ABC with these vertices. I'm going to go ahead and graph it. And it says find the image after the dilation centered at the origin with a scale factor of 2. So what the scale factor does is it takes every value from AB, from the points A, B, and C, and multiplies it by 2. So our A prime, and I'm going to do this in a different color, sorry. Our A prime would be 0, 4. Our B prime would be 4, 0. And our C prime, when we multiply this by 2, would give us 4, 6. So I'll go ahead and graph that. And that's our enlarged image. It has a scale factor of greater than 1, so it should be bigger. I also had those mislabeled as B and C, so I changed those really quickly. Okay, then it also says do it with a scale factor of 1/2. And I'll change my color. What you're going to do with that 1/2 then is multiply everything by 1/2. So our A, I'm going to call it double prime, is 0, and 2 times 1/2 is 1. Our B double prime will be 1, 0. And our C double prime, when we divide those by 2 or multiply by 1/2, we get 1 and 1 1/2, or 1.5. So I will graph those really quickly. And I did shade that in so you could see that a little bit better, but there's your A prime, C, B prime, double prime, and C double prime. And that 1.5, you would go over at 1, up 1.5 to be able to get that point. Okay, on example 4, it says determine the scale factor for the dilation, then determine if it's a reduction or enlargement. Or a congruence transformation. It tells us that the small one here is our pre-image. So to find the scale factor, if you remember, we have to take the image to the pre-image. So I'm actually just going to count the distance here from the image, and you can count that. It's 6 over the pre-image, and that looks like 1, 2, 3. And that's what R will be. So R here is 2, and because it's greater than 1, we say that it is an enlargement. And we can see that it has gotten bigger. On the second one it says EFG is the pre-image, so it looks like we're starting with something bigger, getting smaller, so we should find out that it is a reduction. To find R, again, we're going to find a side that's easy to measure. I'm going to choose this side, and we're going to take the image first from A to D and count that. It's 4 over the length from E to G, and we can just count that. 6, and then we'll reduce that and we get 2/3. So we can see that because that's less than 1, it's called a reduction. Okay, on the last one it says find the measure of the dilation image S prime T prime or the pre-image ST using the given scale factor. So it's going to give you one or the other. Here it's given us the actual image is 20/3, and it's going to ask you to find ST. So if we take the idea that R is always a comparison of the image, in this case it would be S prime T prime, over the image. I think I said that wrong. The image over the pre-image. And so R here is 4/3. This is equal to my pre-image over ST, and I'm going to call it X. And there are a couple ways to do this. I like to teach the cross multiplying to get that X over here. So I have 4/3 X. And or another way to look at that instead of saying it like that. Let's just get rid of X because it's in the denominator. We're going to multiply both sides by X. So you have 4/3 X equals 20/3, and then because we're solving for X, we're going to get rid of this fraction. There's two ways to do it. You can either divide, or I like to flip and multiply, and that will cancel everything out there, and we get X equals over here, the 3's divide out, and 20 divides by 4 5 times. So with that conclusion we get ST will have a length of 5. Okay, you may have to do that the other way. It may give you ST instead, and you'll be looking for S prime T prime. That's what you'll call X. Anyway, good luck with your assignment. It's 10-2, rotations and dilations.